Press. Alright, so we're going to talk about a device called a transformer. Kind of drew one here. Basically, a transformer, just used as an example of mutual induction, where we have two coils. This is our primary and a secondary coil. And the wires are actually wrapped around an iron ring or a donut. So this is iron, which can be magnetized. So if we have a current in the primary coil, let's call that IP, the current in the primary coil, that'll create a magnetic field. Just the current going through the coil creates a magnetic field. And normally that magnetic field would kind of spread out, just like a little solenoid. However, the iron coil causes them to loop around, follows the iron. And so in the secondary coil, we draw it this way where it's on the other side. It doesn't really have to be, but that's the way we drew it. And so all these magnetic field lines that are generated by the primary coil loop around and go through the secondary coil. Now, that's the assumption that we're going to make, that these magnetic field lines just form perfect loops. If you're an engineer, you want to be a little more specific. There's going to be some leaking out and whatnot. But for practical reasons, transformers can be built with very high efficiency. So it's not a bad assumption. Here, I'll write down the assumption here. Let's call phi to be the flux through a single coil. And this is any coil. So it could be a coil in the primary or in the secondary. And what we're going to assume is that the flux is the same through each coil. So they have the same area. And basically the number of magnetic field lines, it doesn't matter where the coil is or where the loop is. We're just assuming these magnetic field lines just circle all the way around so that they go through every loop. Okay, so what happens, let's say we just had a battery here and we created a current in this coil. There's going to be a flux through the primary coil and a flux through the secondary coil, but nothing would happen if this was just hooked up to a battery. Because we have a flux through the coil, but that doesn't do anything. Or I'll write down Faraday's law. So in Faraday's law, you get an EMF if there's a changing flux. And so what we're going to do is we're going to hook our primary coil up to an alternating current. So that squiggly line, that's a symbol used for an alternating current. And so if the primary current is constantly changing, this magnetic field is constantly changing, and we have a changing flux in the secondary coil, which will drive a current in the secondary coil. Okay. And we want to apply Faraday's law to this. So first, let's look at the EMF in the primary coil. And again, we're just looking at magnitudes. We don't care about that minus sign. Now the flux, let's say the primary coil has NP turns. So the number of turns, we'll just call that NP. And in the secondary coil, we have NS. So the total flux through the primary coil would be the number of turns times the flux through a single loop. And the EMF in the secondary coil same thing, except we look at flux in the secondary coil, different number of loops. Now again, we have this delta symbol, so we're taking a difference of a product of two things, and we've done this a few times before. So if one of these things is constant, like the N, the number of turns, that's not going to change. So we can take that out. Okay, and we can take that NS out here. Okay, so what I'm going to do now is I'm going to divide the top equation by NP. So if we divide the EMF in the primary coil divided by the number of turns in the primary coil, we get delta phi over delta T, where phi is just the flux through a single loop. Now if we do the same thing for the secondary coil, if we divide by NS, we get the exact same thing, and so these two things have to be equal to each other. And we can rewrite this. I want to write it the way it is in the notes. So again, you can write it either way. Okay. And so this is basically what a transformer does. And this is what makes alternating current so useful. Because it's not that complicated of a device. At least I'm just describing a very simple transformer. If you look at our electrical grid, they've got some fairly complicated, they're a little more complicated than what we're talking about here, but they're doing the same thing. So let's say our primary coil is plugged into a wall outlet. So the EMF for the primary coil, let's say that's 120 volts. That's what you get for just plugging something into a standard outlet. And the EMF in the secondary coil, we can just I'll write that here. We can solve for the EMF in the secondary coil, and that would just be, if we're plugging it into a wall, 120 volts times, this is the turns ratio. Like the number of loops in the secondary coil over the number of loops in the primary coil. And the thing is, this is pretty easy to set to whatever we want it to be. So if you have a device, like say your cell phone or something, you're plugging it ultimately into an outlet to charge it. You can also plug it into a USB thing, but usually you can just directly plug a device into an outlet which is at a potential of 120 volts. But the device might not want 120 volts. Usually they want a much lower voltage. And so let's say you have a device here. Let's say this device is designed to use 20 volts. So it would be very easy to plug this into an outlet. What you do is, the person who designed this device would probably expect you to plug it into a 120 volt outlet. If it's designed to be sold in America. Other places have different standards. But what you do is you just build a transformer into the device. Sometimes it's built into the power cord itself. Like in a computer, you've got that little box. Different devices, sometimes they've got something, the power cord itself can do it. But somewhere in the device, between the wall outlet and the actual working part of the device, you drop the voltage, and all you have to do is build a transformer with the right turns ratio. So in this case, you'd want a 1:6 ratio. This would be called a step-down transformer. If you're going from 120 volts to 20 volts, that's a step-down transformer. So you want that turns ratio. You want NS over NP to be 1/6. 120 over 6 is 20. That will give you the right voltage for your device. So one way you could do that is have one coil in the secondary and one loop in the secondary coil and 6 loops in the primary coil. That would do it. Or you could have 2 and 12 or 3 and 18. Now, engineers might find a difference between like 1 loop and 6 or 2 and 12. There could be other factors involved, but ultimately you just want that turns ratio. And again, this is a very important application of alternating current. Yeah, if we did not have this, you have to wonder, how are we going to, like how would you use a device that requires 20 volts? Like, would your house just have to have a lot of different outlets that are receiving power at different voltages? But with alternating current, you can change these very easily, just by building a device called a transformer. And so we can have just one standard for your house. The energy that comes into your house, it's at 120 volts. And whatever device, it can raise or lower it as needed. Okay, there's another use we're going to talk about in a minute, but let's talk about these currents. So remember, power is current times voltage. And in this case, voltage is just electromotive force. So we're assuming a perfect transformer where there's no energy lost. Now, in reality, we can build them with like over 90% efficiency, so it's not that bad of an assumption to assume that there's no loss of energy. There's always a tiny amount, but significantly over 90% efficiency. We can safely ignore it for what we're doing here. And so, if we look at the primary coil, we have, I can get rid of this example. So the power delivered to the primary coil would be the EMF of the primary coil times the current, and that's equal to the power delivered to the secondary coil. So again, we're just assuming perfect efficiency here, and we can write that that would be IP over IS, the current in the primary over the current in the secondary. And so we can combine all of this into one big equation. I'm going to put like this. Okay, so yeah, we've got this first equation, NS over NP, but that same ratio is also equal to IP over IS. So again, for a perfect transformer, these are all equal to each other. So again, it's a very nice thing because it allows us to have a standard in America, 120 volt outlet. So the person designing a device that's intended to be plugged into that outlet, they can just build it, a transformer into it, and convert to whatever they need. Now, if you go to Europe, they're 240 volts, or I'm not sure the exact number, might be 220, but yeah, they have a higher voltage as their standard, and so you can use a transformer to build like an adapter, so that it'll convert that down to the 120 volts that were expected. So you have the outlet and then this adapter, and then you plug your device into the adapter, and that adapter converts it to 120 volts. There could still be some issues though, because there might be power differences. Yes, like the 220 volt outlet might provide more power than you want. So that could be a separate issue. But yeah, they do sell those adapters that can be used. Okay, so now I want to talk about another thing that's really important about transformers, and then there's our power grid. We have a power plant which generates electricity. Actually, I'm going to look it up. There's a nice picture in the book. If I can find that real quickly. Yeah, so it's a nice, oh, there's actually a couple pictures. So yeah, these are the actual transformers, like an actual picture of a transformer. Very large, see the person standing there. So they're very large. But here's a picture where we've got a power station and showing the wires that eventually lead to your house. So there is a direct connection between you and the power station. You're like your house and the power station. Now, when it comes to transmitting power, you saw that energy is dissipated in the form of heat by carrying current through a wire. Unless it's a superconducting wire, but those are very expensive, and they only work if they're very cold. At least for now they do. So that's a significant problem. And the longer the wire, the greater energy loss. So again, you're miles away from the nearest power station, so you could be losing a lot of energy, and it's inefficient and wasting resources. And so they want to send the power as efficiently as possible. And it turns out that sending energy at a very high voltage is more efficient. So the power plant, let me see if it's listed in this book. Yeah, it says this is 12,000 volts. So we have a power plant here, which is at 12,000 volts, which is pretty high. You do not want this going into your house. However, this is not efficient enough. There'd be significant energy lost. So then what they have is a step-up transformer. I'll just throw an upward arrow. So what that's going to do is convert that to 240,000 volts. And so these are these very high energy power lines, or high voltage. Theoretically, there's no energy difference. But so what happens if you step up the voltage, you're dropping the current a lot. And that's why it's more efficient to do it that way. You just have a lower current. Okay, so now we can transmit power very efficiently, but the problem is you don't want this wire, this 240,000 volts going directly into your house. That's not exactly safe. So when we get to like your neighborhood, there will be a step-down transformer. Again, I'm going to look at this example in the book. That turns it to 800. I'll just draw the wires. That goes to 8,000 volts. So again, still too much to go into your house, but then it can branch off. We have like another step-down transformer that's going to go convert it to, it's interesting, the picture here says 240 volts. But then it goes directly into your house. So like here, I think at this point, it would branch off in different directions. So like this is going to houses. So there'd be probably a sequence of, if you look at the whole grid, you'd have all these different branches where 8,000 volts are going kind of close to your house, and then it splits up. So there's like a house here, then it goes to the individual houses. And it says 240 volts here. Kind of interesting. I know houses actually have, they typically do have some 240 volt setups as well. Like usually if you have, maybe a refrigerator requires higher voltage. So maybe that's why it's 240. Actually, the actual power transmission, it uses 3 lines, and they're not something we go into in this class, but they're out of phase with respect to each other. And so you can combine them in different ways to get 120 or 240 volts out of it. So, but anyways, so like this is your house then. So you have the appropriate voltage. So like out of the whole thing, this is the longest part here. These are those high voltage lines that are either underground or, up on those see them when you're driving along the road. You see these all the time. They definitely put these out of reach of people because you don't want to touch them. Very high voltage, very dangerous. Yeah, sometimes they put them underground. They're safer there, but I guess harder to access if you need to repair them. But yeah, so again, this is a huge part of our power transmission, which relies on transformers, alternating current. So you can't do this, what we're talking about with direct current. Now, I did learn that part of our power grid actually does use direct current to transmit power. So I haven't looked into this too thoroughly, but what I'm assuming they do is they probably switch it to alternating current to, to adjust the voltage, because you can switch back and forth between direct current and alternating current. So maybe they use a direct current just for the long distance and then convert that to an alternating current and use a transformer to lower the voltage. I'd have to look into that, but I kind of recently learned that they use direct current in some cases to transmit power. But yeah, transformers, really, really important. This is something that does not exist with direct currents, that you can just easily transform one voltage into another. So that's why alternating current is so prevalent, and it's also good for this power transmission, and it's also like kind of how we naturally make things by spinning turbines. But yeah, again, we're looking at kind of just a simple example of a transformer. But yeah, this is basically what we need to know. That assumes a perfect transformer. Okay, so that'll be it for this one.